Živjo, pozdravljeni in pozdravljene na temni strani Lune. To je že 50. epizoda, torej jubilejna epizoda, in zato se bomo tokrat tudi malo zavrteli. Pogovarjali se bomo namreč o rotaciji zvezd.
Oddaljene zvezde se nam mogoče zdijo dolgočasne in nespremenljive pike na nebu, ampak v resnici so prave kozmične plesalke. Čisto vse, brez izjeme, se vrtijo okoli svoje lastne osi, nekatere počasi, druge pa precej divje. Seveda se vrti tudi naše sonce, na katerem lahko rotacijo opazujemo preko potovanja njegovih peg. Nebo je tako kot nekakšen oder, na katerem zvezde izvajajo vesoljske piruete. Današnji gost, Diego Godoy Rivera, raziskovalec na Inštitutu za astrofiziko na Kanarskih otokih, nam bo razložil, zakaj se zvezde vrtijo in kaj se lahko iz tega naučimo o njihovi starosti.
Poleg intervjuja pa boste izvedeli še nekaj zanimivih novic in nekaj tudi o novembrskih opazovanjih. Najprej pa prisluhnimo današnjemu gostu.
Our guest today is Diego Godoy, an astrophysicist from Chile who's now working at the Institute of Astrophysics of the Canary Islands. He studies how stars spin, age, and generate magnetic fields, and he's using tools like gyrochronology and astroseismology. His work helps us understand how stellar rotation shapes everything from magnetic activity to the conditions around distant planets. Diego, welcome to our podcast.
Hello, thank you so much for having me. It is an honor to be in your amazing podcast. And thank you for the opportunity to discuss what I work on a day-to-day basis.
Oh, very nice. So let's start. So we know that stars in the sky look like very tiny dots that never change, but we know that it's not true. And one of the things that we know is that they spin. They rotate around their own axis like dancers spinning in pirouettes. So why do they spin and how fast do they typically spin?
So the question as to why stars spin, really the answer is they are spinning now because they were always spinning in the past. So this is kind of an inherited property that stars have in some sense. So stars form from these giant clouds of gas and dust. They are enormous, like I think like over 1,000,000 times the size of the star. So the cloud that the sun, our own star, the sun formed from, it was 1,000,000 times larger than the sun. And this gigantic cloud had a little bit of a property that we call angular momentum. So that is the technical name. But this is just to reflect, just imagine this has a little bit of rotation in it. Very small, even if it's very, very, very small, this thing is so huge that when the star eventually forms and, millions and billions of years go by, this cloud collapses and forms the star. And the star is so much smaller than the initial size of the cloud, like 1,000,000 times smaller, than any initial, even slightly greater than zero amount of rotation that the cloud had, then collapses onto a very, very small size, which is the sun in this case. And then, so this angular momentum property that we say is kind of transferred to the star. And so the classic example that we give in this is the figure skater or the ice skater that is, dancing and spinning and jumping on the ice. And if she takes a little bit of impulse and starts spinning around herself, if she has her arms extended out outside, she's going to be spinning at one rotational velocity at every whatever x seconds. And then if she contracts her arms and pulls them closer to her body, then she's going to start spinning even faster, because angular momentum is being conserved. So it is the conservation of angular momentum is this relation between how rapidly you spin and how big you are. If you're big, you spin slowly. If you're small, you spin more rapidly. So stars spin now, and spin, you could say, relatively rapidly, because before, and now they're small, they spin rapidly, but before they were much bigger and they used to spin slowly. So this is why they spin. And how fast do they typically spin? This is just to keep a number in mind. Even though we don't see it, and it's actually I don't know. It's some of the things that blows my mind is that um, maybe if they didn't tell us, we wouldn't notice that the sun is spinning. It's just every day it looks the same, more or less, no, for our eyes because we cannot look at it directly. But using instruments and techniques, we can see that the sun does actually rotate around itself. On average, it rotates around itself every 25 to, let's say, 27 days. It actually depends where you are on the star or in the sun in this case. So the equator is a little bit faster, and the poles are a little bit slower. But on average, let's say the sun rotates about every 25, 27 days. I think it's the number. This is the sun now. When it was younger, it was rotating much faster, like let's say every 10 days. So it has spun down, and we'll get into the details of why that is. Um, and really, it depends also what type of star you talk about. So a star like the sun right now rotates about every 25 days, but more massive stars rotate more rapidly when they are younger. Um, they rotate more rapidly, and then lower mass stars can rotate more slowly if they're old. It really depends when you look at them, but there is kind of this relation of more massive stars being more rapid rotators, lower mass stars being more slow rotators.
Very nice. So now we learned that everything rotates in space.
Yes.
Yeah. So you mentioned our sun. You mentioned that we see star spots that rotate faster on the equator and slower around the poles. So why? How can this happen?
This is really because the sun is not a solid body. The sun really is a sphere of plasma. Is this fluid? So like if you take a tennis ball and you spin it, basically it's going to spin like a solid body. Now the whole thing spins together. But so it takes the same time for the poles and the equators of the tennis ball to go around itself at the same, to do one revolution. It takes up the same amount of time. The sun is not a solid body; it's a fluid. It's a ball of plasma, and it has a convective envelope on the outside. So it really is not such a nice and order kind of thing. So just imagine if you had a ball of water, a sphere of water, and then you try to spin it, then water is gonna spin at different velocities depending on where it is. So this is the reason why. It's because it's not the ideal case. It's a fluid. Yes.
So we can directly observe it in the sun. But what about other stars? Does it happen there as well?
Yes, so this happens in other stars. It's more complicated to observe. So, for example, for the sun, if you take the light of the sun, um, um, you can even see the imprint of the spots. But for the things that we call sunspots for the sun, for other stars, the analogs, we call them star spots. So there's just these dark kind of on the surface of the star. We see these dark marks, these dark regions. They are typically associated with regions of high magnetic fields, and we see them. Well, we don't actually see them, but we see their impact on the other stars because when we take any random star and we stare at it constantly, say we observe any random star like the sun for a whole month, we're going to see that the brightness ever so slightly decreases and then increases and then decreases and then increases because the star is going to have these star spots on the surface, which are dark. So they take a little bit they kind of decrease the brightness of the star when we have them looking at us on the front of the star. But then if the star rotates, when the star rotates, the spots are going to come kind of to the dark side, to the opposite side, where we're not going to see them. So then the brightness is going to be a little bit higher. And then when the spots come back facing at us, the star is going to decrease the brightness again. So this is why we get this signal. We call it spot modulation. So there is a modulation, there is a repetition pattern due to the star spots. This is one way that we observe them. This is with photometry, which we can do for thousands of stars at the same time, depending on the mission. For example, Kepler and TESS, Plato will go on this line. Another technique is called spectroscopy. So you take the light of a star, you disperse it, and then when you see the different what we call spectral lines, the shape of the line depends on the rotation of the star. So a star that is more rapidly rotating is going to have very broad lines, and a star that is more slowly rotating is going to have narrower lines. So this is another way to do it. It's a little bit more complicated because then you have another factor, which is the inclination. But anyway, that's kind of a detail, but it depends how the star is oriented with respect to you. But to give you an idea, for example, the rotational velocity of the sun is about 2 kilometers per second. So a more massive star, they can rotate like over 100 kilometers per second on the surface. So it really depends. But spectroscopy is another technique, and then there is another technique which has only been done for smaller samples of stars. I think it's order 100 stars for which this has been done, uh, which is to do astroseismology, to study the oscillations of the stars. So stars with convective envelopes oscillate like the sun. And basically, rotation can change the pattern of these oscillations. So it's what we call splittings. But basically, you can think about the oscillation pattern of the star is slightly, very slightly distorted by the oscillation, and but this requires very, very precise measurements, very expensive measurements, and this is why we only have them for few stars. But those are more or less the ways in which we can measure the rotation periods or rotational velocities of stars.
And you mentioned before that, however, over a long time, stars, as our sun, will spin down, right? And the question here is why? So they are getting older and more tired as dancers, or I don't know why they are slowing down in time.
Right. So here we go back to the key quantity that we described earlier, which is angular momentum. So basically, the amount of spin that they have in them. Stars, slowly but surely, stars like the sun, are shedding away this angular momentum. So tiny pieces come out slowly. Why? Because stars like the sun, they eject particles. They have like we call a solar wind. So if you have ever seen the aurora borealis, those are just energetic particles from the sun, from the solar wind, that just happen to fall down the earth. They follow the magnetic field lines, and this is where we see them. I have never seen one, by the way. I really want to. But the point is that the sun is constantly ejecting these particles all the time. And moreover, in the sun, in the outer layers, we have convection. So the energy transport mode is convection. So we have these kind of bubbles of fluid going upwards and inwards of the sun. And all of this motion in the star generates magnetic fields because these are charged particles. Charged particles moving generate magnetic fields. So when these particles are ejected from the sun, they carry away some of these magnetic fields. Basically, they carry it away up to some distance. They carry it with them as far as they can, but at some point they cannot carry it with them any longer. So at this point, angular momentum is being lost. Slowly, it's a small amount because the sun is losing mass, but very, very slowly. So this is why they spin down, because they lose angular momentum, because energetic particles take away some of these some of this quantity. Yes.
So I think this directly brings us to the tool you're using that's called gyrochronology. That's directly related to what you just described. So can you please tell us a bit more about this method and what is it useful for?
Okay. So the analogy that I like to use here is if I show you a picture of a person, you can more or less guess the age of the person, right? You can tell if it's a kid,
Yeah.
if it's an adult, if it's an ancient person. You can more or less guess the age, maybe within 10 years. With stars, that's not really the case. So stars, maybe a little bit of context here. Stars spend most of their lifetime in what we call the main sequence. So the stable phase in which they burn hydrogen into helium. This is what the sun is doing, and it's only halfway through that. After that, other things happen. We can talk about it. But basically, stars spend most of their lifetime in the main sequence. And in the main sequence, think about your life. You take a picture of you now and think about this is what you're going to look like for 70 years out of your 100-year lifetime. So during those 70 years, there's basically no way of telling how old you are. You can be 5, you can be 10, you can be 67. So this is the case for stars. They change very little during the main sequence. So we are trying to do, we as astronomers who want to know the ages of stars, I'll get into this in a second, but we want to find ways of telling the age of star. Like how can I crack this code? How can I know your age? And rotation is one of these quantities that slowly but surely changes as a function of time, as I described earlier. So basically, we study how fast is the star rotating when it's young, when it's medium age, and then when it's older. And then we map this what we call age rotation relation. And that is the tool that we call gyrochronology. So gyro refers to the spin, chronology to a chronometer. The idea is to use the rotation as a chronometer to tell the age of star. And on the other hand, why do we care about the ages of stars at all? Like, why is this important? This is important because perhaps when I give outreach talks, the most sincere reason that I can think about is because for me the question of whether are we alone in the universe or not is something that sometimes keeps me up at night. Like, and the thing is that regardless of the answer to this question, yes or no, like both freak me out. Like, are we alone? Yes. Are we alone? No. Okay. So we can take this with whichever way, and they will both be super fascinating. But to find this life, we're going to need to find, we're starting our search by something that we know, which is ourselves. So we're looking for Earth like planets around Sun like stars. And let's say we find a planet with all the new telescopes, with James Webb. We find a planet that looks exactly like the Earth. It has the conditions suitable for life. Even let's say we find some signatures of life. Are they real? Are they not real? One of the first questions that we're going to ask is how old is this planet? And basically, because here on Earth, life has very much changed as a function of how old the planet is. We as humans have only been around for, a few millions of years, but the planet is billions of years old. So knowing the age of a planet is very important. So thinking about this again to the fundamental question of are we alone or not, if we find a planet like the Earth on another system, we're going to ask the question: is this how old is this planet? And planets form together with their stars. So we're going to then ask the question: how old is this star? So how do we tell the age of a star if it doesn't change? Well, we can try with gyrochronology. So this is why it's so important.
Now, speaking about stars, I wonder. I mean, basically the stars found the holy grail of remaining young for a long period, or still trying to look young for a longer period, right? So they can do it. They can do it. However, my question was, how do you calibrate this method? So, speaking in other words, how do you know what is the initial rotation period of a star? I mean, are the initial rotation rates or periods similar across stars of different masses, or are smaller, larger? So what is determining the initial rotation period of a star?
So let me start with the last part of that question. So I should say that we have been talking about gyrochronology and stars losing angular momentum in a predictable way. This is the case for stars like the sun. So basically, stars, depending on how massive they are, have different structures really. So if we go to a star like the sun, it has a radiative core and a convective envelope. And the reason for this is just how energy transport works. A star of this mass, of this size, will behave like this. If we go to more massive stars, it's actually really interesting because it's the other way around. They are so massive that they have convective cores and radiative envelopes. Those massive stars, they rotate rapidly and they remain rotating rapidly for their entire lifetimes. So they rotate at, if the sun rotates every 25 days, these stars can rotate, a day or below 1 day. So they are kind of like, like the crazy kid in school that's always, doing crazy things and rotating around himself. So that star is doing that thing the entire life. So for those, it's hard to use gyrochronology. But for stars like the sun, we can use gyrochronology. And then going to the part of how do we calibrate this? So what does calibration mean? Calibration mean kind of training where you know the answer. So we need to have systems where we know independently the age, which is hard to get, and the rotation period, which is also hard to get. But the age arguably is even harder to get. So what systems can we use where we know the ages? Let's start with the hardest part of the question. This is where, for example, the sun is quite useful because we know the age of the sun, not because of its rotation, but rather because it's information coming from studies of meteorites that form together with the solar system. And by studying the chemical composition, this goes beyond my expertise, but people can tell the age of meteorites. So we have at least one anchor point. We have one calibrator, which is the sun. What other calibrators do we have? Other calibrators, for example, are stars that form in star clusters. So basically, stars that have formed together and that have remained together up to their current age. So for these stars, and Marusha would be an expert on this, for these stars, we can know their ages by independent methods of rotation. For example, basically, we study their shape on the luminosity versus temperature diagram, and this can tell us how old a given family of stars is, how old a star cluster is. So many of the studies of calibration of rotation have been focused on star clusters, and this is actually what I spent most of my PhD thesis on. So we grabbed samples of stars that were forming clusters that had rotation periods, and we used those as calibrators. There are other, even crazier ideas to calibrate rotation. And I've also done some work on this. So, for example, one idea is okay, so you have a cluster, which is a system of stars, a family of stars. You have many stars, hundreds. Let's take this to the extreme. An extreme would be, for example, just a cluster with two stars. So we call this a binary system. So for stars that are in binaries, that are in certain conditions, so far away enough from each other, such that they evolve as single stars. So think about this like, you have a, it's like a family that forgot that they're together, but you can still tell that they are family. So for these stars, if we get to know the age of one star, well, we can apply the age to the other star because they form together. And so in this way, we can do it. So for example, stars in special systems like white dwarfs, which are stellar remnants, for those kinds of systems, we can use them as well as calibrators. But basically, people like me, we bang our head against the wall, trying to think of ways in which we can calibrate gyrochronology, how we can know stellar ages independently of rotation. Yeah.
Super interesting. But now, so you spoke about binary stars. So I wonder, do they behave? Does the rotation behave differently actually? Because in my understanding, this is a complex system. So there are two stars. Each of them has their own spin, and then they're also rotating around their center of mass. Is there any like transport of angular momentum or between each other, or how does this work? Are they just like independent, or is this different?
Right. So fantastic question because the answer really depends on basically how far away they are. So, and this is crazy. The first time I learned this, like I couldn't believe it. They are binary stars that were formed together that are gravitationally bound to each other that are almost one parsec away from each other. So this is, 200,000 times the
Wow.
distance from the Earth to the Sun. They can be super, super far away, but we ever so slightly can tell that they are moving together through the sky. And they have, orbital periods of millions of years. So these are systems that are so wide that we're never going to see them orbit around each other. in our lifetimes. It's basically
Mm-hmm.
where,
Mm-hmm.
in 100 years they have barely moved across their orbit. But then if we take the same binary system and we shrink the orbit, so we put them closer together and closer together and closer together, we will reach a point where they will start to feel each other. And this is what we call tidal interactions. So basically, they stop behaving um, just like a point mass, and they start becoming like 3D bodies to each other. Um, and for example, this is taken to one of the extremes is the interaction between the Earth and the Moon. No, so we say that the Moon is tidally locked to the Earth
Mm-hmm.
because the combination between their masses, their sizes, their separation is such that the Moon feels the Earth, and the Earth, of course, feels the Moon. But the Moon is always giving the same face to the Earth. No, so
Mhm.
these kind of situations can happen when the orbit shrinks enough such that you start to have these tidal interactions. At what point does this happen? More or less, we have seen evidence that when the orbit is below 10 days, so when they orbit around each other in less than 10 days, that is when you broke the system. This is the rotation of the star, of each star, is no longer the rotation that it would have if it were alone. And we need them to be alone to be
Mm-hmm.
useful for gyrochronology. So
Mm-hmm.
uh, it's a complicated dance, really, but we are finding binary systems in all kinds of separations, wide separations, small separations. So there's a little bit of everything out there.
Mm-hmm. But what about in case there is a planet, for example, you have not two stars in a binary system, but star and massive planet of, I don't know, at least few Jupiter masses, let's say. Do you, and for example, you mentioned earlier that you use clusters as calibrators. So, for example, if you know the age of this star from a cluster, and then you see that it's behaving a bit differently than expected, then can you find this object suspicious in a sense that there might be a planet present? Is this can you actually see this effect?
This is fascinating because we expect, like you just said, basically a binary star, or I will rephrase as one of my colleagues always says: a star with a planet is just an extreme binary system where one of the bodies is just really really small, which is the planet. No,
Mm-hmm.
so basically, if a star, for example, swallows a planet, that will modify the angular momentum of the star because the planet is bringing angular momentum with it to the star. So when will this matter? It will depend, really, again, kind of the same situation as with the binaries. It will depend how far away they are, how massive the planet is. Um, but it can happen. And actually, there are colleagues trying to, I think the name, instead of gyrochronology, what they called it was tidal chronology. So basically, a gyrochronology revised by the tidal effects that you could have had. And this tidal
Mm-hmm.
chronology depends on, again, how massive the planet is, how far away it is, or how far away it was, how much angular momentum brought with it, and so on.
So, you mentioned at the beginning that one of the ways of looking at stars and trying to get some information from them is also to look at their sunspots. And even if they are far away, we can see the variations in brightness of those stars. And the variation in brightness is really, really small. It's one on 1,000, right, or something
Yes.
like that. But what kind of so how do you collect data? What kind of telescopes do you use? What kind of technology is used in that case? So
Yes.
yeah, what do you use to and to collect all this data?
So to collect this, we need what we call high precision photometry. So basically, a telescope that cannot only collect light but can make distinctions between very small changes in this light. Like you said again, it's like about we need to be able to distinguish about 1 in 1,000 changes. So imagine, if your height is 1.70 meters, you need to disentangle 1/1000th of this. So, a fraction of a centimeter. So you need to be able to measure really, really tiny changes in the star. And for this, it's easier to do it from space. And it's easier to do it also if you observe the star for a long time, for a long, long period of time, because you need to observe the star at least, for a full cycle of the rotation. So you need to leave enough time for the spots to be on facing you and then go away and then come back to facing you again. So, for example, the gold standard for this was the Kepler mission, named after the astronomer Kepler. And that was launched by NASA in 2009, and it observed the same field of view for 4 years. So this is the gold standard. We have high precision photometry for a sample of stars for 4 years. Then other missions have come around, like for example TESS. The TESS mission is another high precision photometry mission. It's more limited than Kepler in the sense that it doesn't really stay in the same place. TESS observes all over the sky. So basically, we have you have a month of data here, a month of data, in 2 years, and a month of data in 1 year after that. So it's really messy, and it has been complicated to use this for rotation. But then, for example, ESA will launch another Kepler-like, Plato-like mission, which is going to be called, TESS-like or Kepler-like mission, that is going to be called Plato. And Plato is being launched at the end of 2026, so in about 1 year, which is also going to collect this high precision photometry.
So a lot of new data is coming. Very exciting. For the end, I have one mysterious question. So you explained nicely how stars spin down as they age. They rotate slower and slower. But on the other hand, we know that after stars die, they become white dwarfs or even neutron stars. And we know that, for example, neutron stars spin very, very fast. For example, we know millisecond pulsars, in case if geometry is right, which means that they rotate super, super fast. But you said that they slow down as they age. So why is that? What's happening here?
Right. So basically, the answer to this, I think, is the same answer as my first answer. So why is a star like the sun rotating? It's because it was always rotating, even before there was a star. When it was just a cloud of matter, of gas out there, that cloud collapsed, and that made the star spin, at 20 something days. But then, when stars leave the main sequence and they become stellar remnants, they collapse again. So they reduce in size by a large, large fraction. So, a white dwarf is about the size of the Earth. A neutron star is even smaller. So it's about 10 kilometers. So imagine collapsing the mass of the sun into the size of the Earth. So just for reference, the sun is the radius of the sun is about 100 times the radius of the Earth. So imagine collapsing all of that angular momentum into such a tiny region like the Earth, or such a even tinier region like a neutron star. So this is why they spin up. Is because the same process is happening. The parental body, if we call it like this, the parental body was much bigger. So when it collapsed, what is left is much smaller, and therefore it must spin up. It's the same example of the as the as the ice skater that we discussed in the beginning. Um, yeah.
It's somewhere at the back of my memory that rotation periods for low mass stars, probably just M dwarfs, is bimodal. Is this some? Did I remember this correctly, or is this something strange from the
Yes.
internet?
Yes. Oh, Marusha, we could talk a whole other hour about this. This is fascinating. So first, let me
So tell us more,
before
please.
yes. So before going to your question, let me tell you about something that we don't really understand yet, which is I said a very massive star has a convective core and a radiative envelope. It doesn't spin down. Then we have a star like the sun, which has a radiative core convective envelope and it spins down. Then if we take this to lower masses, we get to the M dwarf regime that you just mentioned. And M dwarfs They're so low mass that their mass is so little that they are fully convective. They don't even have the mass to have a reactive core, so they are fully convective. So they also spin down, but we think in the sun that one of the key components to generate the magnetic field in the sun is what we call the tachocline. So the tachocline is this transition
Hmm.
between the reactive core and the convective envelope. So that we think is a key component to having all the spin down process, basically. But M dwarfs don't have a tachocline, but we see M dwarfs spinning down. So we don't really know why on earth do M dwarfs behave like sun-like stars, even though they are different. They lack a key component, something that we think is a key component, but they still spin down the same way. And going a little beyond that, they have the same kind of rotation activity relation. And so now going to your point, so it's true that M dwarfs have bimodal distributions. Basically, the lower the the lower the mass of the star, the faster they reach very long rotation periods. Um, so, for example, at 4 giga-years old, the sun is rotating at 25 days. An M dwarf, low mass star, more low mass star than the sun, at the same age will be rotating, I don't know, but let's say 70 days. So kind of the discrepancy between rotating rapidly and rotating slowly becomes more extreme as we go to lower masses. And so for M dwarfs, we see not in clusters, which are young, but out there in the field, we don't know their ages, but we see M dwarfs with rotation periods of like 100 days, 120 days, 150 days. And these are out there, and we see them. It's hard to measure, but they are out there. At 150 days, again, you need to be observing them for a long time because you need to let the signature come back and come in and come back and come in. So we see M dwarfs that are very young that rotate rapidly, few days, 10 days, and then we see these M dwarfs at 150 days. So um, it is true that they have a bimodal distribution in this sense. They have kind of a more extreme behavior. Um, but why do they have the same rotation activity relation as sun-like stars? We don't really know. Like this is something where you didn't expect it to happen, and yet it is there.
Yeah, it looks like a big mystery.
Yes. Yeah, yeah. It's a big mystery. Mhm.
What other mysteries are there for the
Uh,
stars that we don't know about their
mhm.
rotation?
So many. So, this is one of the points that I remember that I wanted to mention before. So, basically, the question is: can we apply gyrochronology to any star? Or I think Marusha even said, when we look at clusters, do all the stars behave the same? And the answer is no. Of course, it's going to be no. Like life is never easy. Okay. Um, if we take a population of, let's say 1 billion years old stars, they all were formed at the same time. They're all cousins and siblings. They have the same chemical composition, the same age. They're in the same region in the galaxy. We would expect them to form this sharp pattern in their rotation. But we have outliers, so stars that don't really belong to the bulk population. And we are sure, and this is part of what I spent many years of my PhD on. We know that they belong to the cluster because we did a very careful study of trying to remove what we call contamination. So you have a visitor from another house that just happened to be at the family dinner at the time you took the group picture. Okay, but this guy is not from the family, so we can take him away. We did this, and still some of the outliers remain. So there are physical processes out there that make stars not follow the pattern. Uh, Mostly they can be rotating more rapidly. Could be planets, could be binaries, as we discussed, could be something else. For example, chemical composition is a good reason of why this can not be the case. Um, and okay, so that is one problem. Well, that is one of the problems of gyrochronology, that when you expect it to work perfectly in star clusters, it works quite well, but not perfectly. But now let's take it. Let me give you even more bad news for gyrochronology. So even more bad news. I have two of them. One of them it's something that people have called the stalling. Basically, if stars spin down as they age, two stars that spin at the same rotation period should have the same age, no? Because it's just a continuous process. However, it was found 5 years ago at this point that this is not always the case. Sometimes it can happen that during periods of time, stars that have different age will actually rotate at the same speed or at the same period. Why? This has not been fully confirmed, but I think we have solid evidence to support that what is happening is that stars have angular momentum inside them. And basically, sometimes, well, let's go back to the sun. Radiative envelope, radiative core, convective envelope. So these two components of the sun, you can think about it as two shells. They can rotate at their own speeds, at their own velocity. They try to match each other, but they can get decoupled because the envelope spinning down via these magnetized winds, the core is not spinning down. It is transferring angular momentum to the envelope, so that spins down the core. But basically, what was found is that when this transition happens, when the star becomes kind of a more unified type body, when the core matches the envelope, depends on the mass of the star. And different stars do this matching at different ages. So it was found that, for example, stars, K-type stars, so think 70% the mass of the sun, at 700 million years rotate the same as K-type stars, 70% of the mass of the sun, at 1 billion years. So even though they have slightly different ages, the rotation periods are the same. So, and this we think is due to internal angular momentum transport. This is called the stalling, and we're still trying to understand what's going on. So that was bad news number two, we could call it. Now I have bad news number three, and so those two, they are bad news, but they are not critical news. Bad news number three is this is getting silly now. So what's happening, or what people have been what people have found, this is about 10 years ago, is that when you go to stars older than about the sun, so past halfway of their main sequence lifetime, so let's call it 40 years or old or older for a person, let's say, more or less, they are rotating more rapidly than we expect them to. So this is
Oh
called
no.
the this is called the weakened magnetic braking. So instead of being just a regular magnetic braking, it's weakened. So it's a more weak version of the magnetic braking. And it's actually so weak that you could explain it in with the models in theory by setting that no angular momentum is being lost. So just imagine, it's like your hair is turning gray until about halfway through, and then it stays like this, and it just stays like this for the rest of it, for the rest of your life. So what is happening here? And this is we go back now to the field of open questions. So we don't really know why this is happening. Again, this is based on a small sample of stars, of all stars for which we know their ages independently of their rotation. So we're talking again 100, 200 stars. So this is yet to be fully confirmed for every star out there in the universe. But one of the ideas that people are working on is saying, okay, something is happening really to the magnetic field of the star, and not just the magnetic field, but the shape of the magnetic field. Basically, the topology. So what we call the topology of the magnetic field. The idea is that a star like the sun or younger stars have a kind of a large scale magnetic field, usually a dipole. But then, so just imagine a large scale magnetic field. But then, when stars become older, the idea is that these magnetic fields become more complex, such that you no longer have a large scale magnetic field. So you still have the magnetic field there, but it's broken up into smaller versions of it. So these Um, lower intensity of magnetic fields, more complex topology could cause the star to stop shedding away this angular momentum. So it's still losing mass slowly, but those particles are no longer carrying away such high amounts of angular momentum, and thus the stars remain spinning at the same rate as they were when they were younger. This is very much work in progress, and I'm very excited. I hope in my next 2 years to work on this, because this is I would say the key open question that we have right now in this field.
Yeah, so you presented this as bad news, but I think it's good news because you can do a lot of exciting research on this.
Yeah. So, Diego, thank you for joining us today. Actually, it was really amazing to hear about all these, all these stars and their properties. And actually, I believe that I will now look at the night sky and try to picture the Dancing with the Stars show every time that I will look at them. So, yeah.
Yes, yes.
And stellar rotation, as you mentioned, so stellar rotation is maybe something that we do not first think of when we look or think at stars. But yeah, today we have seen that it's very important, and it has a lot of open questions that are still still have to be answered. So thank you very much for presenting this topic to us.
Thank you so much for having me. I get really excited
And see
talking
you
about
in a few
this.
years, right?
Yes, for sure, for
And
sure.
see you
Yes,
in a few years.
yes.
Okay, very good. Thank you. Thank you.
Thank you.
Thank you.
V vesolju se res vse vrti in še v glavi se mi zdaj malce zavrtelo. Maruša, daj povej nam, kaj si novega zasledila glede novic o vesolju?
Ja, zasledila sem, da se tudi okrog Zemlje stvari vrtijo. Namreč odkrili so novo kvazi luno Zemlje. Opazili so namreč majhen asteroid z imenom 2095 PN7. To so znali avgusta letošnjega leta. In ta objekt na Zemljo gravitacijsko ni vezan, ampak vseeno okrog Sonca potuje na tirnici, ki je zelo podobna Zemljini. In tako se daljši čas, to je lahko tudi na 1000 let, nahaja zelo blizu Zemlje. Ta objekt je zelo majhen, verjetno ima premer le okrog 30 metrov, in zato so ga opazili šele sedaj, ko je zelo blizu Zemlje. Namreč na svoji tirnici se lahko od Zemlje zelo, zelo oddalji, ampak trenutno je zelo blizu. Njegova trenutna oddaljenost je primerljiva s tisto do Lune. Samo kot zanimivost, oddaljenost Lune je približno 380.000 kilometrov. In ta objekt so zaznali s primerjavo fotografij, ki so jih posneli z observatorija Pan-STARRS na Havajih, kot že rečeno, letošnjega avgusta, in potem so to primerjali z arhivskimi posnetki in so ga odkrili tudi tam. In skazalo se je, da je bil ta objekt tam na slikah že kar nekaj časa in da Zemljo verjetno spremlja že vsaj nekaj 10 let. Zakaj so ga odkrili šele sedaj? Pa zato, ker je zelo, zelo temen, je zelo, zelo majhen in ga je zelo, zelo težko odkriti. In po trenutnih izračunih bo v okolici Zemlje ostal do leta 2085, takrat pa naj bi ga gravitacijske interakcije, po domač povedano, vrgle iz orbite. Tako da, ja, trenutno seznam zemljinih kvazilun šteje že 7 članov. Med njimi sta tudi Kardeja in Kamo-Oaleva. Ostale lune imajo pa taka imena, da jih ne bi brala, so samo številke in neke črke. Tako da ostanemo pri tem. Mogoče bo tudi ta novi objekt 2025 PN7 dobil eno bolj lažje izgovorljivo ime v prihodnosti. In ja, seveda vprašanje, od kje je ta kvaziluna prišla. In ena izmed možnih razlag je ta, da je to fragment naše lastne prave lune, ki se je odkrušil takrat, ko je nekaj drugega trčilo v luno. Po drugi strani pa lahko ta objekt izvira iz pasu asteroidov. Zaenkrat še ne vemo. Najlažje bi to ugotovili tako, da bi posneli spekter tega objekta in analizirali njegovo kemično sestavo, ampak ker je ta objekt zelo temen, je to praktično nemogoče. Ampak po drugi strani je pa eden izmed teh, se pravi Kamo-Valeva, še posebej zanimiv. To pa zato, ker je maja letos kitajska vesoljska agencija proti njemu izstrelila vesoljsko sondo Tianwen-2, ki bo leta 2027 na njemu nabral vzorce kamnin in jih prenesel nazaj na Zemljo. In tako bodo lahko ugotovili njegovo kemično sestavo in se naučili nekaj več o izvoru tega objekta. Tako da že čakamo na novice.
Ja. Jaz pa tokrat nimam novice, imam pa povabilo, in sicer za vse, ki se ukvarjajo in se ukvarjate z astronomijo in izobraževanjem. Vabljeni ste, da se udeležite spletnega dogodka, ki se imenuje IAU in letos poteka že 7. leto. Gre pravzaprav za delavnico astronomiji v izobraževanju, ki jo prireja Mednarodna astronomska zveza. In letos bo delavnica od 18. do 21. novembra. Takrat boste lahko sledili zanimivim predstavitvam in se srečali z učitelji in astronomi celega sveta. Delavnica poteka na daljavo, vpis je prost v resnici, torej ni potrebnega nobenega plačila, je popolnoma zastonj. In predavanja se ponavljajo z zamikom, kar v bistvu omogoča udeležbo z vseh koncev sveta. Glavni temi letošnje delavnice sta izobraževalna tema, ki je osredotočena na poučevanje z uporabo pravih astronomskih podatkov, in znanstvena tema, ki je letos posvečena galaksijam. Predstavljeni bodo tudi drugi prispevki o izobraževanju in astronomiji v šoli, s primeri iz prakse za osnovne in srednje šole, tudi nekaj prispevkov o raziskovanju na področju izobraževanja z astronomije in o učnih metodah in možnih uporabnem orodju za izobraževanje. Vsi posnetki so potem kasneje tudi na voljo na YouTube kanalu Pisarne, kjer najdete ravno tako tudi posnetke preteklih srečanj iz preteklih let. Povezavo do spletne strani in do preteklih videoposnetkov bova dodali v zapiske. Prijava je možna do 21. novembra, torej do zaključka tega spletne delavnice. Dogodek podpira Shaw Prize Foundation v sodelovanju z Pisarno za astronomijo v izobraževanju, ki deluje pri Mednarodni astronomski zvezi IAU. Zaradi premika ure konec oktobra nastopi sedaj tema že popoldne in zato je večerni del noči daljši. Novembra namreč zaide sonce že pred 17. uro in to pomeni, da so pogoji za opazovanje neba ugodni že zgodaj zvečer. Novembra na večernem nebu kraljujeta Jupiter in Saturn, ki sta vidna večji del noči. Saturnovi obroči so sedaj nagnjeni tako, da jih z Zemlje gledamo v bistvu skoraj strani. In omenim naj še, da se bosta Saturn in Luna nekoliko bliže srečala v soboto 29. novembra, 2 uri po zaidu sonca. In ta prizor boste lahko opazovali nad južnim obzorjem. Torej, planeti so običajno dovolj svetli, da jih Luna ne moti. Ostala šibkejša nebesna telesa, ki bi jih radi opazovali, pa tudi zvezde, če bi se radi po njih orientirali, raje opazujemo okrog Mlaja, torej teden prej in teden kasneje. Recimo. Takrat je Luna še najmanj moteča na nebu in svojo svetlobo ne povzroča pretiranih preglavic. Luna bo v Mlaju 20. novembra. Med prizori na nebu, ki jih omenja tudi knjiga Glej k zvezde, ki jo najdete v zapiskih, je meteorski roj Leonidov. Ta novemberski meteorski roj bo viden v noči iz 17. na 18. november. Meteorski roj Leonidov sestavljajo prašni delci periodičnega kometa Tempel-Tuttle, ki se v bližino Sonca vrača vsakih 33 let. Povečano število meteorjev, ki mu pravimo meteorski dež, smo nazadnje doživeli v letih 1999, 2001 in 2002. Običajno pride do povečanega števila ob prihodu kometa bliže Soncu, kar se bo zgodilo sicer šele leta 2031. Vse ostale vse ostale spletne povezave, kjer lahko najdete torej prelete mednarodne vesoljske postaje ali pa sončevo aktivnost, najdete v zapiskih. Z vami sva bili
Maruša?
in Dunja. In to je bila že 50. epizoda podkasta Temna stran Lune.
Nasvete in vprašanja sprejmeva na naslov podcast.temnastranlune@gmail.com. Poiščete pa naj jo lahko tudi na družbenih omrežjih. Podcast je praktično povsod Temna stran Lune, napisano vse skupaj in brez presledkov.
In če želite, lahko podcast tudi podprete na spletni strani ko-fi.com, poševnica Temna stran Lune. Hvala vsem, ki ste to že storili. Nabrani prispevki bodo služili predvsem nakupu opreme, od mikrofonov do slušalk.
Podcast je del mreže aktivnosti Zavoda Kozmolab, ki se ukvarja s promocijo in popularizacijo astrofizike. Hvala Peliju iz sosednjega podcasta, opravičujemo se za vse nevšečnosti, ki je prispeval glasbeni uvod in zaključek.
In slišimo se čez mesec dni. Srečno!
Adijo!